Hello everyone, welcome to the submodule on quantum key distribution in QNE. In this submodule, we're going to look at a very fascinating applications of quantum networks. This is, of course, the quantum key distribution. We're going to have a brief overview on the protocols, the different metrics used in this protocol, as well as run it in the QNE website. So let's jump ahead. The goal of this protocol is to establish a secret key between two parties. Now, why would anyone do something like that? Consider a scenario like this, where we have our two players, Alice and Bob. Now, they want to send messages with each other, but they don't want their message to be leaked out to an eavesdropper. What they do for this is they'll encrypt their message, which is a fancy way of saying they're going to lock their message using a key. This will be sent to the sender, by the sender to the receiver, and the receiver is going to use the same key to unlock that message and read it. QKD tries to create this key so that the players in this protocol will be able to share the same key so that they can use it to maybe, for example, encrypt their message, send it, and decrypt it. Now in quantum domain, you can apply this QKD protocol in two ways. You can either use it by just transferring qubit straight up, or you can also use entanglement. That will facilitate the process of key distribution. In this submodule, we're going to look at the later part, where we create entanglement, distribute it, and then try to form a secret key with it. Let's look at the two quantum resources or quantum topics that we're going to come across in the submodule. The first one is, of course, sharing and generating entanglement. For this, we use the EPR pair. Alice and Bob will create an entangled qubit pair. If you don't know what entanglement is, think of entanglement as a connection between two qubits that is not actually affected by the distance between them. Even though if they are far apart, they may be connected in some form. For this protocol, we're going to assume the belt state 0, 0 plus 1, 1 as our EPR qubit. The next topic that we will come across in this submodule is the topic on measurement. As you might be aware, a single qubit can be represented in a Bloch sphere. Think of measurement as taking a look at the state of this qubit. In quantum information, measurement is done according to a basis or an axis. If you say you want to measure it in the z-basis, you're actually measuring it through the z-axis. And once you measure it in the z-basis, it will collapse into one of the states at the end point of the axis. So if you measure it in the z-basis, you collapse it into either 0 or 1. Similarly, if you measure it in the x-basis, you collapse the qubit into one of either plus state or the minus state. Now keep in mind, measuring in different bases may provide different result. For example, measuring qubit 0 in z-basis, if there are no noise in your operation, will always result in a state that ends up in 0. However, if you measure the same qubit 0 in the x-basis, you might end up in the plus state half of the time and in the minus state half of the time. So it's worth remembering that measuring in different bases might actually give you a different result, even though you have the same qubit. Now that you're familiar with the two main topics in this submodule, entanglement and measurement, let's go ahead and see how the protocol works. The first step in the QKD protocol is to establish n number of EPR pairs between Alice and Bob. This n is computed by Alice and Bob beforehand, so both of them realize how many entanglement qubits they should generate. The second step is that Alice and Bob measure their part of the EPR pair independently in either the z or the x basis. Now keep in mind, they don't share which basis they measure in right now. So they measure it in their own particular basis, they store the result, and both of them are kept secret just for now. In the example shown below, Alice has measured her first qubit in the x basis and have gotten result 0. Bob, on the other hand, has measured his qubit in the z basis and has got the result 0. In the next step, however, they keep the measurement results to themselves, but share the choice of measurement basis. So Alice and Bob each share their choice of basis one another at the same time. In the step 4, Alice and Bob throw away the results from rounds where they didn't measure on the same basis. They are only interested in the rounds where they measure in the same basis. In step 5, of the remaining results, Alice randomly chooses half of them for the purpose of testing. So this message would go something like this. Alice would say to Bob that she would like to test the measurement result she got in, let's say, the qubit round 3 and 6, and she would also share the measurement result with Bob. Bob gets the measurement basis and will reply back with the results he got for his corresponding EPR pairs. This is carried out to calculate a metric called the quantum bit error rate. QBER mathematically can be calculated as the number of mismatches in your test measurement batch over number of entries in the test measurement batch. You'll find that when you run your QNE application in the website, this metric will be shown. This is a very important metric because if the value of the QBER goes below a value that both Alice and Bob had said before, then they would realize that there is some kind of eavesdropping going on. They would then just discard all the measurement and all the EPR rounds they have done so far, and they will retry it from the beginning. Now in step 6, after step 5, if Alice and Bob decide that the value of QBER is less than the value that they have designed before, then they will continue on using and creating the secret rock key. Consider this example. Here, Alice and Bob share 6 EPR pairs. They see that EPR pair 1 and 4 are measured in a different basis, so they will discard it, which is shown in the red boxes. Alice will mention to Bob that she would like to test the measurement results of rounds 3 and 6. And she'll keep the measurement results of rounds 2 and 5 for herself. Bob will also share the results of measurement rounds 3 and 6. A summary of this is shown in the table below. For the test results, Alice has results as 1 and 1. However, Bob has results 0 and 1. This would mean that there is one mismatch in their test rounds, and since they have 2 rounds, the QBER is 1 over 2 or 0.5. Alice and Bob, however, will recreate their rock key based on the rounds 2 and 5, which is 1, 0 for both of them. If Alice and Bob are happy with the QBER result that they've got, they'll take their secret key and perform privacy amplification techniques, and then create their full secret key. This has been a summary of the QKD so far, and now we're going to take a look on how QKD works in our QNE web platform. Now that we understand how quantum key distribution works, let us see how it works in the Quantum Network Explorer site. So if you go to quantumnetwork.com/application, you get to see a lot of community applications that were developed in-house as well as by developers all around the world. Now, because we are using quantum key distribution, let's launch the app. Here we can see different networks that we can select. Right now I'm just going to select Europe, and I'm going to assign Alice to Paris and Bob to Delft. You can do that by just dragging and dropping the roles specified. As a next step, we can see how we can configure the networks present in this. Not only can we configure the nodes, but also different properties of the channels present in this network. I'm going to set it as default and then go ahead to the next step. In this step, we can choose the number of EPR pairs we want to generate initially. Right now, I'm just going to keep it as the default number, which is 10. And then we click the next step. This step gives you an overview of the application that you're going to run in QNE. We have our network as Europe. We have our two roles defined with the place that they're going to be in, as well as the application-specific configurations. In this case, the number of EPR pairs that will be generated, which is set to 10. Let's go ahead and run it. As we click on Run, this job will be sent to the QNE backend. Right now, it is being simulated using a simulator called NetSquid. So the wait that you see right now is now completed, as the simulation has finished and the results have returned to the front end. Let's go ahead and see the results. You can click on Load Results, and that will give you a full overview of the results that the backend has given you. From the presentations beforehand, you should have seen that Alice's results corresponds to the whole number of EPR pairs that she has generated, along with the measurement basis that she chose. It also gives you metadata on whether the measurement basis that she chose was actually the same measurement basis that Bob had chosen. We will also store the measurement outcome for all the measurements we have done beforehand, and also see for the test cases whether or not they have got the same outcome as Bob. This is repeated in the case of Bob as well. So in case of brevity, I'm not going to explain the whole table again. Finally, we have the whole metadata that corresponds to how Alice measured in which basis where, and also the similar for Bob. The final statistics are also given here, in which we talk about the measurement basis, number of pairs compared for the outcome 2, and also the QBER, which you should have known by now. Finally, we also talk about the row key that Alice and Bob has generated, and this is displayed here.